Okay, great. Welcome everyone to the Statistics Former Student Network webinar. We are very fortunate today to have with us Dr. Tatiyana Apanasovich. She's an associate professor of statistics at George Washington University. She earned her PhD in statistics from Texas A&M University in 2004. Her advisor was Dr. Ray Carroll. And prior to joining George Washington University in 2012, she held positions at Cornell and also Thomas Jefferson Universities. Her research interests include functional data analysis, statistical genetics, measurement error modeling, and spatial statistics. Her research has been funded by the National Institute of Health and National Science Foundation. She's here today to talk to us on new classes of multivariate covariance functions. So take it away, Dr. Apanasovich.
Oh, hi, everybody. Thank you so much for such a great introduction. Thank you so much for inviting me. I cannot be more excited to present my work. I'm really happy. I mean, it's virtual. I would love to visit Texas A&M, but I always have really warm feelings when I speak about Texas A&M or when I meet my classmates or professors. So I only have really warm memories about my time in Texas A&M. And I visited Texas A&M a few times after, but I haven't been back in years. So I'm looking forward to coming, I guess, for a conference. So thank you so much for, again, inviting me to give this talk. And today I'm going to talk about new classes of multivariate covariance functions. Here's the short outline of my talk. First, I will introduce the area of spatial statistics. I will talk about geostatistical modeling. I will introduce spatial processes. Throughout the talk, I will discuss properties of and characteristics of spatial processes, challenges in modeling, different modeling assumptions when we model such processes. My special interest in covariance functions, which a majority of the talk will be on covariance functions. I will discuss different families of covariance functions. I will focus on Matern and Cauchy families. And this talk is on modeling multivariate covariance functions. So the heavy theoretical part will be on that topic. And I plan to also go over an application and numerical status if the time permits, and I will finish with the discussion. So in many scientific fields, such that environmental science, geology, ecology, epidemiology, data are collected at spatial locations. And also, such data may include multiple variables measured at locations. And I have a few examples. For example, in the agriculture or hydrology, soil properties such as pH, nutrient content, texture, they can be measured at different points in the agricultural field. Air pollutants, for example, PM5, nitrogen dioxide, and others can be measured at different sites in the city. And if in the field of ecology, ecologists measure species richness, like such as number of species, different characteristics of species, abundance, and so forth at various sites in the forest. And for those applications, researchers can ask the following questions. So what about, for example, what are the underlying environmental factors which explain the observed patterns of species in the forests? Or how does pollutants, multiple pollutants, affect health outcome in, say, people who live in the city? And can we predict soil properties at sample locations based on the nutrient measurements or soil measurements that we have and at some limited number of sites? And when we talk about spatial statistics, I just mentioned really traditional applications: ecology, environmental science, climate science, agriculture, forestry, but also we have emerging applications, for example, genetics. So genotypes and gene expressions can be measured at various locations in tissues and organs. Here we have a set of special nature of the data collected, and also we have multivariate data points, as we can measure different genetic characteristics or other biological and clinical characteristics of those tissues. And a new, really interesting application, smart cities, where researchers are interested in designing cities which are best suitable for humans to dwell, and they collect data on air quality, temperature, and so forth at various sites in the city. And also sports statistics, where the researchers collect spatially locations of players, locations of balls, baseball, basketball, and then also on a specific player, they collect other observations, such as the heart rate. So with respect to shots, they collect the speed, direction, and other characteristics. Sorry, I keep scrolling down the wrong way. So to understand complex patterns and relationship in this data, multivariate spatial data analysis is required. And multivariate spatial analysis includes techniques that account for both spatial structure and multivariate nature of the data. Again, the spatial statistic itself, the focus of spatial statistics is modeling data which have spatial locations attached to the data. And the multivariate spatial statistics, instead of just observing a univariate data point at the spatial locations, we have a vector. And we also assume that the observations within the vector are related to each other. So they have some non-trivial complex relationship, and also each of those variables has the spatial nature. So there are relationship between the observations which are measured at nearby locations. And also we have so-called cross relationships, where the observations, they are related to each other spatially. So let's say a nutrient pH measured at one location is related to a another soil property measured at a different location. So we call it cross spatial dependence. And in spatial statistics, we have roughly kind of two kinds of methods. One is called kriging, and the other one is spatial regression. And the kriging is a fancy word for interpolation or prediction, where we predict the values of the observations at locations where those observations are not available. And for the multivariate case, we assume that some values of this multivariate vector are available at locations and some are not. And so we would like to predict the values of observations which are not available at some locations. And that is a really important task, because some of those observations can be more expensive to measure and some less. And so by using cross relationships, we can have better predictions of the variables at unsampled locations. And the other area is roughly spatial regression, and that's when we have outcomes and covariates, and we build a model that links outcomes to covariates. And outcomes have spatial features, so they are measured as spatial locations, and the covariates themselves can also have a spatial nature. And in the multivariate settings, instead of having one outcome, we have a vector of outcomes. And we also assume that those elements of the vectors, they are related to each other, and we have this spatial process, so they are also have some spatial relationships. And again, when we talk about spatial statistics, we assume that the observations which are close to each other spatially, so the distance-wise, so the observations are related to each other. So we have dependence, and if we talk about Gaussian processes, that translates into correlations. So the main challenges in multivariate spatial statistics include modeling spatial dependence. So because again, so the dependence here is not just univariate, the dependence here is cross. So the dependence between elements of the multivariate vector, that dependence can vary in space, and that is challenging to model. So there are computational challenges. So there's a computational complexity associated with such problems, because now the dimension increases. And sometimes, depending on the way we model, we have problems with interpretations of the results. So here is the geostatistical model, and again, I'm talking about multivariate ways, so I will introduce the multivariate version of a geostatistical model, where we have y is a vector, so it's a p-dimensional vector of responses. And in geostatistical model, we present y as the sum of two terms, so-called large-scale variation and the small-scale variation. And oops, sorry. Okay, so the large-scale variation function, mean function, it's a p-variate mean function, and that function can be a function of covariates, which can be measured in space. It also can be a function of coordinates, or both. And that function can be parametric, non-parametric. Usually, if it's a non-parametric, it's a kind of low-order splines. So it's not too flexible, so not to confuse with the small-scale variation. And the small-scale variation z, here, and it's multivariate settings, we have a vector of z. So it's a p-dimensional vector of spatially correlated errors. And here we assume that the stochastic process has a mean 0. And also the covariance structure such that if we pick two locations, so function k has two indexes, ij, so that k sub ij, x1 and x2 is the covariance between the ith element of z measured at x1 and jth element of z measured at x2. So for so here, if we want to complete the model, we need to specify the probabilistic model on Z. Again, our model has a deterministic part and a probabilistic part, well, stochastic part, and the spatial correlation is being modeled through the stochastic small-scale variation Z. And we assume throughout the talk that Z is the Gaussian random field, so it's a Gaussian random process, and also it's an isotropic process. So the assumption of Gaussianity is not too restrictive. In traditional regression settings, we often assume that the errors are Gaussian, or can be so the outcomes can be transformed to have Gaussian residuals. So there are some results on the cases where Z is not Gaussian, but I'm not really going to talk about them. So again, we assume that the process is Gaussian, so mean is 0. And in this case, the Gaussian process on the whole probabilistic model is fully specified by the covariance structure of this process. And the isotropy means that the covariance or correlation between the element for the same element of the vector, the correlation depends on the distance between 2 points. So again, the correlation depends, and cross correlation also depends on the distance between 2 points. That's not an overly restrictive assumption because locally in smaller in the smaller fields, the isotropy works. It's a good working assumption, and also isotropic models can be building blocks for more complicated anisotropic models. So the modeling of covariance function is important in spatial statistics. Again, when we have this geospatial model, the stochastic component of the model is been introduced through the covariance structure if we assume Gaussianity. But overall, again, generally, the covariance function also is important by itself if we do explorative data analysis on the spatial processes, if you want to understand dependent structures, basically how the observations relate to each other in space, how fast the correlation decay, at which lags the correlation becomes negligible, and so forth. So the estimation and prediction, if we build the model, then the knowledge of covariance structure, the model of the covariance structure, the specification of a correlation function help to build efficient estimates and also efficient prediction. And there's another area where covariance function is also really useful in the sampling design when we try to design experimental design on the field. So the knowledge of covariance function helps us to produce efficient designs. So covariance functions are really kind of special structures. They are objects of research in not just in statistics, but mainly in math, because they have to be positive definite. So not any function can be a covariance function, so it has to be a special function. It has to possess a special feature. And if we talk about isotropic or stationary functions, we have this famous result. It's called Buchner theorem. And Buchner theorem says that the covariance function is positive definite if and only if it's the Fourier transform of non-negative measure. So again, the positive definite property in statistics, we can understand it because pretty much it's linked to this characteristic that the variance of the linear combination of realizations of the field, the variance has to be non-negative. And so that again is translated into conditions on the correlation function of a process Z. So overall, even though we have a criteria, that criteria is not easy to work with, precisely because the Fourier transforms are not easy mathematical objects to operate on. Not every function has a closed form analytical expression for Fourier transform, and so that complicates any mathematical study of properties of such functions. So overall, covariance functions are also not just subject of interest in mathematics. So we use covariance functions not just in spatial statistics. So in many machine learning methods now, the covariance functions are heavily used. And especially multivariate kernels. So there are plenty of examples from the natural language processing where the multivariate kernels used. And also there's an area so-called multitask learning where multivariate kernels are highly desired because they help to exchange information between different tasks. So again, the covariance function, that's kind of statistical term. Another fancy term for covariance function is kernel. And the kernel methods by itself used in statistics, machine learning, and they're really kind of new and interesting applications. I just mentioned the natural language processing, which is a rising area in machine learning and the multitask learning. So next I'm going to talk about special features of covariance functions that we care about, because it's really important to pick carefully the covariance function that would represent well the process that we care about, that we're interested in. And because how well we pick a covariance function, that will affect how good our analysis will be. So again, in spatial statistics, covariance function is important because it helps to produce more efficient estimates. And the specification of covariance function is important for efficiency. In some situations, if we misspecify the covariance function, we can produce the biased estimates. And our covariance functions are tied to processes in space. And here is a place when I would like to discuss which properties of those processes are important and how we can reflect them in covariance structures. And here I distinguish global and local behaviors of Gaussian processes. And at the local, if we think of local properties of the spatial process as the processes which exhibit irregularities. So they're kind of rough fields, they have sort of fluctuations, and then smoother fields, they're smooth, they're kind of nice fields with kind of nice cute curves. And the rough fields would kind of have kind of sharp gradients. And so at the global level, if we think of what are the global features of the process, is the global level, they relate how fast the correlation decay. So whether the observations far apart, they have a significant relationship to each other. And so the local properties of the field, they are related to the behavior of the covariance function when the distance approaches 0, and the global behavior is related to the properties of covariance function when h, the distance, approaches to infinity. So let me start with the global behavior. So the global behavior. So you actually probably heard the term long-range dependence. And so the long-range dependence has many definitions depending on whether you look in the stochastic processes, time series, and spatial statistics. So there is some, I guess, disagreement of what exactly that means. However, they all agree that it has something to do with the memory of stochastic processes. And also informally, the correlation function decreases rapidly. We talk about short-range dependence, and the correlation function decreases slow, and we talk about long-range dependence. So in spatial statistics, we have the formal definition, which we borrowed from time series. So if that integral, and we integrate over a d-dimensional space, if that integral is infinity, then we have long-range dependence. So again, so long-range dependence means the slow correlation decay. And I will demonstrate on specific example, we can relate long-range to short-range dependence to the value of parameters. So if we focus on the parametric families of covariance structures. So the local behavior, when we imagine the fields, So I guess not just imagine if we think of a process from the probabilistic model, we can talk about path discontinuity and the existence of different derivatives, directional derivatives, and we have a really heavy theory that helps us to construct processes with path continuity, path discontinuity, and different number of directional derivatives, and it's called Kolmogorov continuity theorem. So we know a few examples of processes like fractional Brownian motion, which are you can model a specific number of continuous derivatives, and there is a tool to kind of have a pre-specified number of continuous derivatives. However, in practice, generally, it's really hard to visually inspect continuity or discontinuity, or obviously the existence of a specific number of directional derivatives. Again, the probabilistic models, they stem from probably processes which generated. We have physical processes, so we can support such models. If we just visually inspect the fields, it's really hard to see the discontinuities. And there are two reasons. One reason is maybe the scale of our observations, because we observe the process on specific location. The scale is too big, so we can see discontinuity. We can have discontinuities at smaller scale, and also so processes exhibit noise, and noise can mask those discontinuities. And that is why when in spatial statistics we talk about continuity, discontinuity, and we actually refer to in mean squared sense, which is L2 continuous processes. And the path discontinuity is almost sure convergence. And those two convergences, they don't imply each other. So for some bounded processes, they almost surely can apply mean squared continuity, but in general, they don't imply each other. So in spatial statistics, again, we had only one paper that discussed the modeling of spatial processes with the sort of path discontinuity, and since the book of Dr. Stein, we only look at the process continuity discontinuity in L2 sense. So that's sort of when somebody talks about continuous processes or the existence of derivatives, it's mostly in L2 sense. And the mean square differentiability is related directly to the properties of the covariance function. So the covariance function is 2m times differentiable if and only if the sample path has 2m derivatives, continuous derivatives. So there are for our fields, the fields which are continuous but don't have a continuous derivatives, we talk about the fractal dimension or Hausdorff dimension and Hurst effect. So those again are that we quantify the roughness of the field, which is continuous but doesn't have a continuous derivative. And so that also relates to properties of the covariance function when the distance converges to 0. Okay. So here I have a list of families of covariance functions. So again, when we talk about processes which generated our data and how we can match those properties with the covariance structures, and we pay attention to local and global behavior. And currently, in most of the statistical packages in spatial statistics, we have the following families of covariance functions. So we have a Matern, power exponential, Cauchy, spherical, and generalized Whelan, as those are complexly supported. Complexly supported means that they have a compact support. So beyond certain distance, the correlation is exactly 0. Whether Matern, power exponential, and Cauchy, they don't have a compact support. The correlation decays to 0, but it never becomes exactly 0. And in terms of how flexible those families are to model local and global behavior, the most flexible to model local behavior is Matern and generalized Veblen. So they have a parameter. So you can model any degree of smoothness, well, any number of derivatives in L2 sense. And so there are also some models, they have flexible behavior for rough fields. So rough fields are fields which are continuous but don't have the continuous derivative. And that one is Matern, power exponential, and Cauchy. So I specifically mentioned the rough fields because in most of the natural science, the fields are believed to be rough. So then we talk about natural phenomena, climate, or again, environmental science. Again, the scientists believe that their fields are rough. So they're continuous, but don't have a continuous derivative. And that's why they actually do care about the measure of roughness in terms of the fractal dimension. Because again, that number specifies how rough that field is. And so those families can measure. And the only family out of the ones I mentioned that has the long range behavior, so that allows you to model long range processes, the Cauchy, which is again unfortunate because most of the practitioners who model natural processes, they believe their natural processes exhibit long range behavior. There is a new family of covariance functions that appeared last year. And that family has some interesting features. So that family can also account for flexible local behavior. And also it has a potential to model long range dependence. And if we talk about multivariate versions of families, and when I talk about multivariate, I assume the number of components is greater than 2. So this is a literature. So for Matern family, Gnati was the first one who introduced the multivariate version. Then I had a paper in JASA where me and my colleagues we introduced a more flexible version of a multivariate Matern family. And recently, just last year, there was a minor refinement of my model. So as you can see, the interest in multivariate covariance structures is still there. The problems are very challenging. That's why in the last, I guess, whatever number of years, there are not that many papers that are coming out. So I'm in the process of submitting 2 papers on power exponential and Cauchy versions of multivariate family. And there is one family on compactly supported multivariate families. But overall, given the importance of modeling covariance structures and abundance of the applications which possess this multivariate nature, it's really kind of, I guess this is a major gap in spatial statistics because we don't really have an interpretable versions of multivariate versions of existing families. And so here, let me just kind of briefly mention what the spatial Matern is. So Matern family, which is one of the most famous family of covariance function, looks this way. So it has spatial functions, which is the Bessel function, modified Bessel function of the second kind. That function is tabulated, and the gamma function, which also is a function that is expressed as an integral, it is tabulated. So the form itself is a little bit scary precisely because it involves some special functions. So there is a computational toll, I guess, when one uses this family. But the family has 2 parameters in the correlation function, which kind of model the correlation, decay, and smoothness. So alpha is the scale, so it's just you scale the distance, and the parameter mu is the parameter that's responsible for smoothness of the field. So that's the parameter that allows the family to be really flexible when it comes to modeling local behavior. So z is m times mean square differentiable is the parameter mu is greater than m. So this is, again, the biggest attraction of that family, even though, like I said previously, in many practical applications, most of the natural processes, they have mu less than 1, which means that the process is continuous but doesn't have a derivative, a continuous derivative. So the biggest drawback of that family is it can only model short-range dependence. So that's family, it has exponential decay in the correlation function, so which is the short range. For rough fields, that's how we can express the Hurst, the Hurst effect and the fractal dimension. So it is flexible to model long range, local properties for rough fields and local properties altogether, but it only can accommodate short range dependence. And so I just mentioned, so there are a few papers that have been published. The Matern family, again, is really famous, so it was a focus of a few papers, and the multivariate versions appeared. In the Cauchy model, this is the Cauchy model of a correlation function. Well, here it's a covariance function. So it has the following mathematical expression. So unlike Matern, you can see that is a function that does not involve special function, so that's relatively easy to compute. It has extra parameters, so it has a scale parameter phi. So scale parameter means that you scale the distance, so it controls the decay, and it has 2 other parameters. Alpha is the smoothness. So when alpha is equal to 2, the process has infinite number of derivatives, so it's super smooth. And alpha not equal to 2, which is less than 2, from 0 to 2, the process is rough. And we can also express the Hausdorff dimension or fractal dimension as the function of alpha. So alpha is sort of the parameter that controls the roughness of the field when we don't have the derivative, smooth derivative, and alpha is equal to 2, so kind of controls the smoothness of the process. And we have another parameter beta, and that's the parameter that it's additional parameter to model the decay of the correlation, and also it relates to short range with this long range dependence. When the product alpha times beta is less than d, which is the dimension of the field, that the field is long range dependent. So that family is actually deserves attention precisely because for natural phenomena, it can model rough fields really well, because again, it has a parameter that controls the roughness of the field. Also, it has the switch, so the family can accommodate both short range dependence and long range dependence, and it has like the scale and other things. So overall, the family again is gained popularity in practice precisely because finally we are moving away from Matern. And let me go back to positive definiteness and just kind of reinforce the challenges associated with modeling multivariate covariance families. Okay, so remember, we have a vector observed at each spatial location. So our covariance function now has 2 indexes. So this is the block. It's not the whole covariance structure, it's just the block. So the whole covariance structure now has blocks, and each block corresponds to cross covariance. So it's a covariance between ith element of vector z measured at x1 and jth element of vector z measured at x2. Okay, so if we put everything together, we have n times p by n times p covariance matrix, where n is the number of observations and p is the dimension of the vector. So p is how many elements, how many, I guess, nutrients we observe at each location. And n is the number of locations in the domain of interest. So our covariance structure has this kind of block, a block version, right? Each block corresponds to cross covariances. So it's a complicated structure. As a covariance structure, it has to be also positive definite. And so we work with real fields. So it's a linear combination of all elements with real coefficients. So that linear combination has to be non-negative. And as I mentioned before, we have a Bachner theorem that says the covariance function has to be inverse Fourier transform. The covariance function has to be Fourier transform of the non-negative oral measures. So we have the spectral density, which are inverse Fourier transforms of the covariance functions. And for the families of known families, those functions are guaranteed to be positive. So that's no longer a challenge if we pick, if you work with a specific covariance structure family, they are guaranteed to be positive definite. However, for the multivariate version now, those spectral densities, they have to form positive definite metrics. So there's this version of Kramer theorem, again, that states that now when we look at cross-spectral densities and their the number of cross-spectral densities, well, they form a matrix. So I, J, those are the indexes. They go from 1 to P. We have P-dimensional vector. So they have to form positive definite metrics for every value of omega. Okay, so that is a challenging task to demonstrate that, especially if for some of the families, we don't have a closed form analytical expression for the spectral density. When I wrote a paper on maternal family, for maternal family, the spectral density has a closed form analytical expression. It was still a challenging task, but at least at that regard, it was somewhat easier to work with because the function had a closed form analytical expression. So when it comes to the for the Cauchy family, the covariance function, the density does not have a closed form analytical expression. So that possesses specific challenges. So let me just kind of emphasize this. So the goal of that study was to create a multivariate version of covariance function that comes from the Cauchy family. And so this is the mathematical formulation of a Cauchy. And now to create a multivariate version, we need to make the parameters. So the parameters now will be indexed by 2 indexes. And so basically for each field, we will have the marginal Cauchy family. So, and also the cross fields will belong to Cauchy family. So now that's why those parameters have 2 indexes ij. So if I equals to j, it means those are the parameters which belong to marginal Cauchy family, and j where I is not equal to j, those are the parameters for cross covariances. And the goal was, again, to stay within a family and also marginally to allow the margin to have basically any combination of parameters. So marginally, we can allow to have any combination of parameters, but in order to keep positive definiteness, we need to introduce constraints on the parameters associated with cross covariances. And again, this is a challenging task. And for many years, there was only one attempt, and people only produced some sufficient conditions for bivariate. And bivariate is somewhat easier because you only have one assumption to deal with. But even for bivariate, it was a challenging task, and so not all the values of the parameters were covered. And so, my formulation is a huge step up from the previous attempt, because again, we allow any combination of parameters in our marginal covariances, and we constrain our cross parameters. So again, there is no closed form analytical expression for our spectral densities, which should form valid positive definite matrices for any value of omega. So we have to come up with the smart decomposition of our family. And in our decomposition, we have around 4 functions. I just put 2 functions. And so some of them we had to prove their new results on positive definiteness. So I'm not going to, with the time, I'm not going to kind of go deep into that topic of positive definiteness. And here, punchline, so those are the results. That's how our formulations look like. And so again, marginally, the parameters for covariances, they are allowed to be anything. And for alpha, which is the parameter that controls the smoothness of the field, for cross covariances, the parameter, we don't have an extra degree of freedom to model the parameter. It's just the function of existing ones for the marginal fields. The same is for beta. That's parameter that controls the long range and short range behavior of the process. So that parameter also for cross fields doesn't have extra degrees of freedom. However, for scales and for covariances, so those parameters, we have flexible, pretty much anything for the marginal, and for cross, we can have their own parameters. There are some constraints to allow, to force positive definiteness. But in this case, we have a lot of, well, not all, each cross field is allowed to have its own parameter. So each cross field, each covariance for cross field is allowed to have its own scale and its own covariance, with 2 conditions to guarantee positive definiteness for the entire construction. And in application, the one I will demonstrate, we also have sort of a simplified version where we assume that the smoothness of all the fields is the same. So the smoothness of each field plus the smoothness of cross field is the same. There is no extra parameter to model the long range, short range for the cross field, and the scales and the covariances are allowed to be flexible. So we have degrees of freedom to model those parameters for cross fields. Okay, so here's, I have about, I guess, 10 minutes to go over application. So here I picked a data set from so-called Automated Surface Observance Systems, ASOS network, and the data are on temperature, dew point, and relative humidity at 145 weather stations across Texas, Oklahoma, Louisiana, Mississippi, and Arkansas. Okay, so here the blue dots, and so there are some other symbols. So let me explain you what the other symbols are. So the blue dots, they are 125 stations out of 145. They're used to feed the model, and then we randomly selected 20 stations to assess the predictability of our model. So again, the total number of stations considered is 145. 125 stations were used to fit the model. 20 stations were left out to make predictions at those stations and assess the predictability of our model and compare our model with the mature model. So how we fit the model? Well, and as I mentioned before, our geospatial model, geostatistical model has sort of the two terms. It has a fixed effect, deterministic part, and the stochastic part. And the deterministic part can also be modeled as a function of location. And we use the cubic polynomial to remove this trend. And this is the trend, it's a function of longitude and latitude. And then those are QQ plots for the residuals. As you can see, the QQ plots support the assumption of Gaussianity for the residuals. And then we look at the correlations between the dew point, relative humidity. That correlation is pretty high, it's 0.92. And also we have a negative moderate correlation between other pairs, like the dew point and the temperature has a correlation of minus 2.7, and the relative humidity and the temperature has a correlation of minus 5.9. And our model for the correlation, again, we remove the trend, and now our focus is on the spatial relationship at the small scale, and we assume we have the correlation structure which is isotropic. We did plot in the variograms, directional variogram. The isotropy is well supported. And here our covariance function also has so-called nugget effect, which is the measurement error part. So we only see the measurement error when the distance is 0. Well, actually, we don't see it because we don't have replications of the field, but that's the part that belongs to the model because we do assume there is some measurement error associated with the measuring instrument. And there's the functional family here. We look at Matern, and we looked at the generalized Cauchy model that we proposed. So the goal again is to compare the fits between those two models and the predictability of each model. And so here there's some sort of details on how we fitted. The bottom line is the number of parameters. Okay, so we matched the number of parameters to model covariances between those two families. So there are 19 parameters on each. It's not a trivial task to fit 19 parameters. We have a special optimization routine set up to fit these 19 parameters. Since I already had the paper on the flexible Matern family, so I already had the experience with dealing with this, so I just kind of really improved it a little bit for Cauchy. And again, 19 looks a lot, but remember we have 3 fields, and if we just look at just the marginal field, for each marginal field, generalized Cauchy has 5 parameters and Matern has 4. And here I also count nugget, and nugget is only marginal. So pretty much it's 3 parameters plus the nugget and Matern. So 4 plus nugget and Matern is 3 plus nugget. And so for the sake of time, I'm not going to spend that much kind of on the, we fit the model, we obtain the results. And here what we notice, so we assume that alpha is common. So alpha now is 1.96, which is the rough fill. And also when we feed the Matern mu parameter were below 1, actually below a half, that supports the notion of the roughness of the field. So at least those two models, they agree that the field is rough. And so there was agreement in estimating the covariances and the cross covariances and the nuggets. So those measurement errors. So one thing I have to note that when we fit the model, the product the product alpha times beta is less than 2, which means that we do have long range dependence. So for our three fields, for all three, the product alpha times beta was less than 2 again, which is the condition for long range dependence. So the fields, according to our generalized Cauchy model, the fields are rough and they're long range dependent. And the Matern, the fields are rough and Matern only does short range dependent. So it was not possible to assess whether it's long range or not. For the log likelihood, the log likelihoods didn't look too different. So in terms of the log likelihood, we couldn't find a difference between the fits. However, we found a significant difference when we look at the predictions. So for the predictions, again, we left out 20 sites to make our predictions. And so here are the summaries for root mean squared error, and for mean squared absolute error. And just collectively over 20 sites, if we use our Cauchy, we get improvement of for each field around 30%, 16, 30, and 34. And how we calculated it, so it's a difference between the root mean squared error for Matern minus for Cauchy divided by root mean squared error for Matern. Again, and we have those significant improvements if we use Cauchy. Also, we look at individual sites. Individual sites, almost every site had a smaller error for when we use Cauchy family, when we use our family. Again, even so, there's the difference in terms of visual inspection of the covariance function. They look really similar. But what made a difference in place in prediction is the fact that the natural processes are long range dependent. And in this case, this long range dependence actually made a significant difference in prediction in kriging. And we did the simulations where we simulated the fields from our Cauchy model, and we did a lot of other simulations, but specifically we simulated from the Cauchy model with the same spatial configuration. And then we compared the Cauchy with the Matern in terms of the prediction ability, and we got pretty much the same percentages of improvement in the root mean squared error. So for all those three fields, our improvement in the root mean squared error were around 30%. Okay, thank you. And I will take questions now. Thank you.
Thank you, Dr. Apanasovich. Are there any questions? Please let us know. See if I can. There's nothing in the chat yet.
Oh, I don't. So there are questions in the chat?
No, there's not. I was just looking. Any hands raised? Does anyone have a question? If so, speak up. Sorry about that. There's a comment in the chat. Is this also applicable for more complex settings, for example, non-stationary cases?
So the non-stationary case, that's a good question. We can build non-stationary covariances from, it's not directly applicable, but we can use the results to build non-stationary covariance functions. So there are some techniques, some warping techniques, or we can have local stationarity and we can just blend them into globally non-stationary covariance functions. Other?
Any other questions? Or comments? The excellent talk, Dr. Apanasovich. It's a mouthful, sorry.
Thank you.
There's several thank yous in the chat.
Oh, thank you.
Tatiyana, thank you for nice talk, and thank you for your virtual visit to Texas A&M.
Thank you so much for inviting.
Excellent. Thank you, everyone.
Thank you, Marshit, as well.
You guys have a nice spring. I guess it's still a few more weeks of spring before it gets hot in Texas. Hopefully.
That's right. That's right.
All right. Well, everyone have an awesome day. If anybody would like to give a talk at one of these webinars, please let me know or let Elaine James know, and we'll schedule that for a future time. Have a great week.
Thank you.